Welcome. In this session, we will set up a local large language model using Docker Desktop and OpenWebUI with a bundled Ollama runtime. We will begin with a short conceptual foundation and then move into guided demonstrations that you can follow step by step. If anything moves too quickly, please pause the recording, complete the step on your device, and then continue. By the end, you will have a working local interface, a downloaded model running on your machine, and a first reusable assistant configuration created through a system prompt. A large language model is a generative model trained to predict the next token in a sequence of text. In practice, the model does not operate on full words, but on smaller units called tokens. When it generates a response, it relies on the information currently available in its context window, which includes the prompt and the recent conversation. Because generation is probabilistic, responses can vary, especially when instructions are vague or incomplete. For that reason, it is best to treat model outputs as drafts that may be useful, but still require critical review, verification, and common sense. Running a large language model locally can be a strong option when privacy, autonomy, and transparency are important. A local setup keeps processing on your device by default, and it gives you direct control over which model and which version you use. After you download a model, you can often continue working without relying on an external cloud API. At the same time, local inference has practical trade-offs. Performance depends on your hardware, so responses may be slower than in cloud services, and you may need to choose smaller models on typical laptops. The setup also requires a few operational steps, such as installing Docker Desktop and starting a container. A simple way to decide is to consider what matters more in your situation: control and data sensitivity, or maximum speed and convenience. To make this setup reliable across different computers, we use Docker Desktop. Docker is a widely used open source container ecosystem, and Docker Desktop provides a consistent way to run containers on Windows and macOS. The problem it solves is inconsistency. If you install tools natively, differences in operating systems, dependencies, and versions often lead to avoidable errors. Containers address this by running the application in a pre-configured environment. So the same configuration behaves consistently across devices. Docker also makes troubleshooting simpler because it is easy to restart or reset the application stack. On Windows, Docker Desktop commonly uses the Windows Subsystem for Linux, or WSL2 backend. It provides a lightweight Linux environment that helps Docker run Linux containers efficiently. If WSL is not installed, you can install it using PowerShell and then verify it. In the demo section, I will walk through the installation steps and show exactly how to open PowerShell and run the required commands. Once WSL is in place and Docker Desktop is running, we verify Docker and Docker Compose before launching OpenWebUI. In this setup, OpenWebUI and Ollama serve distinct purposes. OpenWebUI is a widely used open source web interface that lets you interact with the local model in your browser and manage prompts in a structured way without needing the command line for everyday use. Ollama is a widely used open source local runtime that simplifies model management by handling model downloads and execution with minimal configuration. You can think of OpenWebUI as the interface you work in and Ollama as the engine that runs the model. For this session, we use a container image that bundles both components, which keeps the setup minimal and reduces installation complexity. We will start the system as a Docker container and access it on our browser at http localhost port 3000. The reason we use this approach is that Docker can run the application in a predictable way across different computers, and it also makes it easy to start and stop the system whenever you need it. To do this, we use a small configuration file called docker compose.yml. You will create this file inside your project folder and then copy and paste the configuration shown on this slide. Think of this file as a simple recipe that tells Docker what to run and how to connect it to your computer. The section called Services defines what Docker should start. We define one service named OpenWebUI. The image line specifies the pre-built package Docker should download and run. In this case, it is OpenWebUI with Ollama bundled, which means the user interface and the model runtime are included together, so we do not need separate installations. The ports line connects the container to your browser. The mapping 3000 8080 means you will open port 3000 on your computer, and Docker forwards that to port 8080 inside the container. That is why the address we use is http localhost port 3000. The volume section is what makes the setup persistent. Without volumes, your configuration and downloaded model files could disappear when the container is recreated. Here we create one volume for OpenWebUI's data, such as settings and chats, and a second volume for Ollama's model storage, so you do not have to download models again after a restart. Finally, the restart setting tells Docker to keep the container running unless you explicitly stop it. After you save this file, you will start everything using one command in the same folder, docker compose up-d. Once it is running, you open your browser at http localhost 3000 and the interface should load. From this point onward, you can close it and return later without starting from scratch because the volumes keep your settings and model files. In this demo, I will install Docker Desktop and then verify that it is working. If you already have Docker Desktop installed, you can still follow along and use this section as a checklist. First, I open a web browser and go to the official Docker Desktop download page. Here, I select the installer for my operating system. If you are on Windows, you choose one of the Windows installers. If you're on Mac OS, you choose the Mac installer that matches your device. Once the installer is downloaded, I start it. On Windows, this usually means double-clicking the installer file and following the installation wizard. On macOS, it usually means opening the downloaded file and dragging Docker into the Applications folder and then starting it from Applications. The first time Docker Desktop starts, it may take a moment to initialize and it may ask for permissions. I will follow the on-screen instructions because Docker needs system-level permissions to run containers. During installation on Windows, Docker Desktop may recommend using WSL2. That is normal because Docker Desktop commonly uses the WSL2 backend to run Linux containers efficiently. If WSL is not installed yet, we need to install it now. To open PowerShell, click the Start menu, type PowerShell, and select Windows PowerShell or PowerShell. For the installation step, it is best to run it as administrator, so you can right-click PowerShell and choose Run as Administrator. In PowerShell, I now run wsl install. I need to create a default Unix user account and set a password. If Windows asks for a restart, please restart the computer. Then open PowerShell again and run wsl-l-v to verify the WSL is now present. If you see a list of distributions or at least a WSL version, the prerequisite is in place. We can now finish the Docker configuration. Now you can start Docker Desktop. When I open Docker for the first time, I need to accept the Docker subscription service agreement. Now create an account and log in to Docker. Finally, I verify Docker from the command line. So on Windows, I can use PowerShell again, and on macOS, Terminal. Please run docker version and run docker compose version to also confirm it prints a version. If both commands work and Docker Desktop shows the engine is running, Docker is installed correctly, and we can proceed. Now that Docker is installed and running, we will prepare the files needed to start Open WebUI. The goal here is simply to create a folder and one configuration file. First, I create a dedicated folder for this project so it is easy to find again later. For example, directly on the desktop, and name it local LLM. On macOS, please open Finder, create a new folder, and also name it local LLM. Next, I create a file named docker compose YML inside that folder. If you have a text editor such as Visual Studio Code, you can of course use it, but any plain text editor is sufficient. On Windows, you can for example use Notepad, but make sure the file is named exactly docker-compose.yml. On macOS, you can use a code editor or a plain text editor that saves as plain text. Now I need to open the file and paste the Docker Compose configuration shown in the slides. This configuration tells Docker to run Open WebUI using an image that bundles Ollama to expose the interface on port 3000 and to create persistent storage volumes so settings and downloaded models remain available across restruts. After pasting the configuration, please save the file. Now we will start WebUI. To do that, we need to run one command in a terminal, and we need to run it in the folder that contains the Docker compose YML file. On Windows, one simple way is to open the folder in the File Explorer, then to click into an empty area of the folder and right-click. Depending on your system, you may see an option like Open in Terminal or Open PowerShell window here. If you cannot see it, try to hold the Shift key pressed while right-clicking. If this also doesn't work, you can use PowerShell again from the Start menu and then navigate to the folder using the cd command. On macOS, use the terminal by pressing Command and space, typing terminal and pressing enter. Then navigate into the folder using cd. Once the terminal is in the correct folder, you run docker compose up-d. The up part means start the services described in the compose file, and the d part means run in the background. The first time you run this, Docker may need to download the container image. That is normal and it can take a few minutes depending on your internet connection. When the command finishes, I can open Docker Desktop and confirm that a container is running. We can now open WebUI either directly on a web browser or from within Docker. On the first launch, open WebUI, which will be displayed in your system language, will prompt you to create a user account. Please complete the sign up and log in. The first account created typically has administrator privileges, which is expected for initial setup. Once you have created the account and logged in, inside the interface, you can, for example, change the language if you click on your user icon and then choose Settings and here Language. It is now important to recognize a few key areas on the screen. The central area is the chat panel, which is where messages are typed and responses appear. Nearby, there is the model control area, often shown as a model selector. At this stage, it is normal for the list to be empty because no model has yet been downloaded. This is important because OpenWebUI cannot generate responses until a model is available and selected. There is also a place to manage chat sessions or conversation history. This is useful for keeping different activities separated. For example, one chat for experimenting with prompts and another one for real work. And finally, there's the settings area, which contains the options for assistant configuration, including system prompts. At this point, the model runtime inside the container will manage model downloads and execution. The next step is to download a model directly in OpenWebUI. Start in the bottom left corner of the interface and click the user icon. In the menu, select Admin Panel. At the top of the Admin Panel, switch to the tab called Settings. Now choose Models, and then at the top right, a little download arrow appears called Manage Models. In the Manage Models view, there's a link that reads, "To access the available model names for downloading, click here." Click this link to open a page on your browser with all the models available for download. For this session, we will use Ollama 3 as the example model family. Ollama 3 is often used in research and higher education contexts because it is designed to be openly available and transparent about its release, which supports reproducibility and responsible use. In practice, the key takeaway is that Ollama 3 can be a strong general-purpose base model for local workflows, and it is available in variants that make local inference more practical. On the Ollama library page, search for Ollama 3 and select the variant that fits typical hardware. If the library shows multiple tags, I would recommend you prefer a smaller or quantized variant for this first download, because it will run more smoothly on a standard laptop. Copy the model identifier exactly as shown. So for example, Ollama 3, 7 billion parameters latest. Return to the OpenWebUI's Manage Models screen and paste the model identifier into the download field and start the download. Now we need to wait until the download finishes. Depending on the model size and your internet connection, this can take several minutes. When the download is completed, return to the chat view. As it is our only model so far, Ollama 3 is already selected. We can now run a test prompt. For example, explain what a large language model is and what it is typically used for. The purpose is to confirm that the full pipeline works. OpenWebUI is running, a model is selected, and responses are generated locally. If the response is extremely slow or the system becomes unresponsive, the most common fix is to choose a smaller or more compact variant of the model and to repeat the same test. Now, the next step is to create a custom model as a reusable configuration. We will select a base model, define baseline behavior through a system prompt, add prompt suggestions for quick personas, create prompt templates for repeatable workflows, and optionally enable web search as an example of an additional feature. A custom model in OpenWebUI is a reusable configuration that turns a general-purpose local model into a tool with a defined purpose. Instead of starting from a blank chat each time, the custom model bundles the most important decisions, such as which base model is used and how the assistant should behave, into a single selectable option. The main advantage is consistency. Once the configuration is set, we can get comparable results without having to remember detailed setup steps. The system prompt is the policy layer of our custom model. It defines baseline behavior that should apply across all interactions, such as tone, level of detail, integrity rules, and a recognizable output structure. Its key advantage is predictability. A clear system prompt reduces variation between responses, encourages the assistants to ask clarifying questions when needed, and helps prevent common failure modes like overconfident answers or invented citations. It does not guarantee correctness, but it makes the assistant's behavior much easier to control and to evaluate. Prompt suggestions are lightweight persona starters that help us begin a chat in the intended mode. They do not replace the system prompt. Instead, they sit on top of it and steer the conversation towards a specific interaction style or task focus, such as active learning support, discussion facilitation, or writing revision. The advantage is usability. We can select a suggestion rather than crafting a long prompt ourselves again and again. Prompt templates are reusable activity prompts that standardize recurring tasks. They are especially valuable in higher education because many interactions follow repeatable patterns, such as guiding critical reading, generating seminar questions, designing practice exercises, or producing structured feedback. Templates improve efficiency and teaching quality by enforcing a stable workflow and a consistent set of headings or steps, and they also make it easier to share best practice prompting patterns with others. Web search integration extends a custom model beyond the model's static internal knowledge. When web search is enabled, the assistant can retrieve up-to-date information and reduce the risk of outdated responses for time-sensitive questions. The main advantage is currency. It supports what's current queries that a local model alone may not answer reliably. The trade-off is that web search can involve external services, so it should be used thoughtfully, especially when privacy, confidentiality, or institutional policy requires keeping work fully offline. So let us now turn our locally downloaded base model into a reusable assistant configuration. Let's create a custom model. Start in Workspace and then open the Models area. Now create a new model and give it a clear name like Academic Assistant. Select Ollama 3 as the base model. So that the assistant uses this local model that has already been downloaded. Now locate the system prompt field and paste the baseline prompt. This prompt is designed to make output structure very recognizable and to apply academic integrity rules consistently. Our system prompt asks the model to write in clear, plain English and to briefly define technical terms whenever they appear. If the request from us is ambiguous, it should ask a clarifying question before answering. Also, it should ensure academic integrity. Do not invent citations, quotations, or factual claims. If it is uncertain, it should say so and suggest a verification step. Also, we don't want it to provide answers that enable academic misconduct. And we also ask for a specific structure. A short descriptive title, a summary of 1 to 2 sentences, and the main answer should be structured into 3 to 5 short paragraphs. And also, we ask it to provide a next step suggestion. Now, scroll down to prompts. We can now add suggested prompts. Add the first suggestion with the name Seminar Tutor. This suggestion is meant to support active learning with discussion and practice. So the persona is the seminar tutor. The focus is active learning support. And we want it to provide clear explanations of course concepts, generate 3 discussion questions aligned with typical readings, create 1 short practice exercise with a worked solution, encourage critical thinking through guided inquiry, and we again define a specific format. In this case, the key concept in 4 to 6 sentences, 3 discussion questions, a mini exercise with a worked solution, and guided inquiry questions. Let's add a second suggestion with the name writing support. In this prompt, the persona is writing support. The focus is structural improvement. We wanted to suggest revisions for clarity and coherence, identify organizational weaknesses in our text, to provide a detailed changelog for transparency, and to never invent citations or factual claims, and not to add any new facts. Regarding the output format, we ask it to create a revised text and a changelog of 5 to 8 bullet points, what was changed and why. Also, we ask for 2 recommendations for improving argument flow. Finally, further down, we can tick the box for web search. Keep in mind that web search can send queries to external services, so use it only when that is appropriate for your context. We can now test our custom model in the chat view. Make sure to select your custom model, the academic assistant, and then test the baseline system prompt without clicking any suggestion. Let's now test the prompt suggestions in a way that makes them practical for real use. If a suggested prompt is written as a complete instruction like we did, clicking it may immediately generate an output without any additional user input. That can be useful in some cases, but it is not ideal for authentic use because the assistant should adapt to a specific situation, course, or learning context. To make that possible, we need to add a simple placeholder that can be filled with a short context description. For this, we need to return to the custom model settings in our workspace and then open the prompt suggestion section. We can now edit the seminar tutor suggested prompt and add an instruction to provide some context. So we ask the user to provide the educational context and then add the placeholder in double curly brackets. Let's do the same for the writing support suggested prompt and then save our model. We can now try the suggestions in a new prompt. Let's assume we want the prompt to work on a first-year undergraduate seminar in educational technology. The topic is local versus cloud AI tools, and the students have read an introductory overview of LLMs. We can then follow along the thinking process and later on prove that the result corresponds to our prompt suggestion. Let us now continue with the third building block, prompt templates. The goal is to store a reusable activity once and then insert it into any chat on demand instead of rewriting the same instructions repeatedly. In this version, the template includes a placeholder for the text again, so that the chat clearly prompts us to paste the text before any analysis is produced. Start by creating the template. Open Workspace in the left navigation and switch to the Prompts tab. Now create a new prompt template and set the title to Critical Reading Guide. The title matters because it is the name that we will use later in the chat to call the template. In the template content field, now paste the following instructions. Notice the placeholder text, which is designed to be replaced by the user with the excerpt or summary. So we ask in the prompt to help us read an academic text critically. Before answering, ask us to paste a text or summarize the argument in our own words, then to put it into the placeholder. In the response, the following headings should be included: the claim, as the main claim in one sentence, evidence, with evidence types and strength, 3 to 5 bullet points, assumptions, counterpoints, discussion prompts, and a next step instruction. Now save the template and test it in a new chat. In the message box, type / and select the Critical Reading Guide template. Now paste a short text that is permitted to use, like this example text on a bring your own device policy. We can now submit the prompt and observe the thinking process and the response. The assistants should now follow the required headings and produce a structured output that includes the claim, the evidence, assumptions, counterpoints, discussion prompts, and a concrete next step. This illustrates the key advantage of templates. They enforce a repeatable workflow and consistent structure, and the placeholder ensures the activity starts with the correct input. As a final step, let us now extend our setup with Retrieval Augmented Generation, or RAG. RAG contextualizes a language model with your own documents, so the model can answer questions grounded in specific material rather than relying on its pre-trained knowledge. Conceptually, RAG works in two steps. The system first retrieves the most relevant passages from uploaded documents, and then it provides those passages as context for the model to generate an answer. The key benefit is that RAG can increase accuracy and reduce hallucinations, especially when you need domain-specific or up-to-date information that the base model may not reliably contain. This makes it ideal for higher education and organizational contexts, for example, using teaching materials, policies, manuals, or also internal FAQs. To use RAG in OpenWebUI, we need to upload documents into the knowledge area and then attach or select the relevant knowledge source in a chat or in a custom model. Once the knowledge source is active, the assistant can retrieve relevant chunks of text from these documents for each question. 3 RAG settings are especially important. Chunk size defines how long each text segment is. Larger chunks preserve more context, but can introduce irrelevant information. Overlap repeats a portion of text between consecutive chunks, so key sentences are less likely to be split at chunk boundaries. Top K determines how many of the best matching chunks are retrieved and provided to the model. A higher value can provide richer context, but it can also increase processing time and sometimes adds noise. Let's now add RAG to our custom model in OpenWebUI. The goal is to ground answers in a real document, so the assistant retrieves relevant passages first and then uses them as context for the response. For this demonstration, I will use a public European document that is easy to download and contains clear, structured content, the EU's ethics guidelines for trustworthy AI, published on the official European Commission resources. Please download the PDF to your computer and remember where you saved it. Before uploading anything, we now need to set the RAG parameters globally. Open the user menu in the bottom left corner and then go to the admin panel. Open settings and then documents. Set chunk size to 1000 and chunk overlap to 200 and select a top K of 5. Now we need to create the knowledge collection. Open Workspace and then go to Knowledge and create a new knowledge collection, EU AI Guidelines. Upload the downloaded PDF. And wait until indexing finishes because the system must process the document before retrieval will work. We now need to connect the knowledge collection to the custom model so that it becomes available by default. Open Workspace and Models and select our academic assistant. Scroll down to the knowledge area and select the EU AI Guidelines collection. Save and update the model and test the RAG setup in a new chat. Confirm that the knowledge source is active for the chat. If not, you can activate it using the plus button and then attach knowledge. Now run a test question. In our case, according to the ethics guidelines for trustworthy AI, what are the 7 key requirements for trustworthy AI? A strong RAG response should stay very close to the document's wording and structure and list the requirements clearly. The thinking process and the model output are useful diagnostic signals. The output did not provide the 7 key requirements, but it clearly attempted to use the uploaded document and it followed the integrity rules from our system prompt. Instead of guessing, it explained that the list was not present in the retrieved context. That is exactly the behavior a grounded setup should produce. It stays aligned with the source and avoids inventing details. When this happens, there are several common causes. A frequent reason is that the missing content is not available as machine-readable text. Many PDFs contain crucial information inside figures, images, or tables. Humans can read these elements easily, but a typical RAG pipeline indexes text. If the 7 requirements are shown in a figure, the index may not contain them at all, which means retrieval cannot return them. Another reason is chunking. RAG splits documents into segments, and lists are especially sensitive to chunk boundaries. If a numbered list is split across chunks, retrieval may only return parts of it, leading to incomplete answers even though the assistant is grounded in the document. A third reason is retrieval mismatch. Retrieval is based on similarity between the question and the text. If the question wording matches an introduction or explanatory section more strongly than the section that contains the list, the system may retrieve the wrong passages. The model then answers faithfully, but from the wrong part of the document. Top K can also matter. If only a small number of chunks is retrieved, the system may not collect enough context to reconstruct a complete list. Increasing top K often helps when answers depend on multiple passages. Finally, formatting and extraction quality can reduce retrieval performance. Multi-column layouts, headers and footers, footnotes, and page breaks can produce messy extracted text, which makes both chunking and retrieval less reliable. The overall takeaway is that RAG quality depends on several factors working together. Whether the document is extractable as text, how retrieval is configured, and how precisely the question is phrased. Let us now apply a concrete fix that targets retrieval coverage and forces a clean reindex. Let's start by taking a quick look at what retrieval actually returned. Open the one source below the response and scan the snippets. In the previous run, the snippets included the chapter introduction and the heading Requirements of Trustworthy AI, but they stopped before the numbered items appeared. This is clear evidence. The model cannot list the requirements because retrieval never delivered the list into the context. So let us increase retrieval coverage in the global settings. Open the admin panel, go to Settings again, and then Documents. Let's set chunk overlap to 300 and top K to 15. The system now retrieves more candidate chunks for each question, and text near chunk boundaries repeats more strongly, and list items are less likely to fall outside the retrieved chunk. Now we need to force re-indexing by rebuilding the knowledge entry. Open Workspace and Knowledge, and open the knowledge collection. And now delete the original document. Upload it again. And wait for the indexing to finish. In a new chat, we can now rerun the exact same test question to keep the comparison clean. According to the ethics guidelines for trustworthy AI, what are the 7 key requirements for trustworthy AI? Don't forget to attach the knowledge base and submit the prompt. We can now validate the improvement directly in the response. The assistant now lists all 7 requirements as distinct items, which shows that RAG is working correctly and that the answer is grounded in the uploaded document. Let's conclude by summarizing what we have achieved throughout this e-lecture. First, a fully local setup was created using Docker Desktop and Open WebUI with bundled Ollama. It provided a simple, repeatable way to run the system on a personal machine and access it through the browser. A local base model was then downloaded and selected, using Ollama 3 as the example, so responses are generated locally rather than in a cloud service. Second, the system was configured for practical reuse. The custom model was created in the workspace to bundle the base model with a clear behavior. A system prompt was used to enforce a consistent response structure and integrity boundaries, so outputs become predictable and easier to evaluate. Prompt suggestions were added as personas to guide users towards specific interaction styles at the beginning of a chat. A reusable prompt template was created and triggered via / command, demonstrating how repeatable workflows can be standardized and applied on demand. Web search was also introduced as an optional feature for situations where up-to-date information is required. Third, the setup was extended with retrieval augmented generation using knowledge. A public European document was added to a knowledge base, and retrieval settings such as chunk size, overlap, and top K were introduced to show how answers can be grounded in specific source material. This demonstrated how RAG reduces hallucinations and improves relevance, while also showing that tuning retrieval settings can further improve accuracy when key details are, for example, missing. The main takeaway is that this workflow is repeatable. It provides a practical foundation for running local LLMs, shaping their behavior through prompts and templates, and grounding responses in your own documents. From here, the next step is to expand, add more knowledge collections, create more prompt templates for recurring tasks, and refine retrieval settings for different document types and question styles.